In this video, we'll talk about the area of a region between two curves. So as you can see in the definition, the area between two curves is given by this integral between a and b of f of x minus g of x dx. Now, why does that happen? Well, let's take a look at this graph that we have here. If we have this f of x is our first function, and the red one with g of x is our second function. If we want to find out the area that is highlighted in green here, how would we do that? Well, we would split it in infinitely many rectangles, and calculate the area of each rectangle. But we learned that in Calc 1, that if we add all those infinitely many rectangles of very tiny width, we actually can calculate an integral. Now, we know that we want to calculate the integral between a and b, but y of f of x minus g of x, why does that happen? Well, if we take a look at this rectangle that I'm going to draw in green, the area of this rectangle is the length. Now, the length is the distance between the f of x graph and the g of x graph. So that distance, right, the distance between 2 points, this distance here, is going to be equal to f of x minus g of x, and then times the width, and this width is actually d of x. So just making a small sketch is going to help you figure out why the formula looks the way it is. So now let's take a look at a few examples. It says sketch the region and find its area. So I'm going to sketch this y equals 2x and then y equal 2x squared minus 4. So please pause the video and sketch it yourself. So I actually sketched in black the 2x, and I sketched in red the 2x squared minus 4. So how do you sketch the 2x squared minus 4? Well, it's a quadratic one, so you find the vertex, which is negative b over 2a, and it's equal to 0, and then the y coordinate is when you set x equal to 0, and you get y equals negative 4, and then I found the intersects, which are plus minus square root of 2. So what do we notice? We notice that these two functions actually, or what do we want to find? We want to find this area, right? So basically, we have to figure out the area between which points. So here it's a point, and then this is the other point. So we want to find the area between those 2 points. So in order to find those coordinates that I mark with blue, I'm going to set 2x equals to 2x squared minus 4, which is a quadratic equation, and I'm going to solve it. So I solve the equation by writing all the terms on one side, factoring the 2, and then factoring the trinomial. If you cannot factor the trinomial, then you have to use the quadratic formula. I made a few review sessions where you can see what's the quadratic formula and how to use it. So basically, what we have here, the integral, the region extends between negative 1 and 2. Now, if we take another look at the graph, we see that the graph of 2x, it's above all the time, above the red one. So the area that we want to find is the integral from negative 1 to 2 of 2x. That's the function when we draw a rectangle between them, then the one that is higher is the 2x. So 2x minus 2x squared minus 4. Make sure you put parentheses because the negative changes all the signs. So then we have just to calculate this integral, which I advise you to pause again and try to solve it on your own, and then unpause and see what I got. So when we open parentheses, we change all the signs, and then I use the antiderivative, evaluate it from negative 1 to 2. So then when we calculate, we get x squared evaluated from negative 1 to 2 minus 2 over 3x to the third evaluated from negative 1 to 2 plus 4x evaluated from negative 1 to 2. So this is going to give us 2 to the second 4 minus negative 1 to the second minus 2 over 3 parentheses 2 to the third minus negative 1 to the third plus 4 parentheses 2 minus negative 1. So we get 4 minus 1 minus 2 over 3, negative 1 to the third, it's negative 1, minus 1, it's plus 1, so 8 plus 1 is 9, plus 4 times 2 plus 1 is 3, so we get 3 minus 6 plus 12, so we get 9. Now let's take a look at the next problem, because the next problem is a little bit different. Here we still have to find the area, but the functions that we have are y equals absolute value of x minus 3 and y equals x plus x over 2. So let's graph them first. Now, when we graph absolute, I always do this. When we graph absolute value of x minus 3, let's think of the parent function, its absolute value of x, so I'm going to shift it 3 units to the right. So it's going to be 3, and then we go like this. This would be absolute value of x minus 3. And x over 2, well, that would be 0, and then go up 1 and over 2, and let me see if it's 2, I get 1 here. Yes, so they do intersect. And so when we connect them, we get something like this. So basically, the region that we want to calculate its area is this one. So how do we find the points? Well, this one is pretty obvious, but we still have to do it mathematically. This piece, it's actually x minus 3, and this piece, it's actually 3 minus x. So in order for us to find this point here, we are going to set 3 minus x equals to x over 2. If we solve this equation, we get 3x over 2 equals 3, which means x equals 2. So this point here, it intersects at x equals 2. The other point, we set x minus 3 equals to x over 2, and we get x over 2 equals 3, which means x equals 6. So we found the intersection points. Now, what is interesting in this problem than the other ones is that if you calculate the area, you get integral from 2 to 6 of the red function, right, which we actually have it. We don't have a name for it, so I'm just going to put x over 2 minus, and then the other function, which is x minus 3 in absolute value dx. So what happens is we actually have two different values. So this x minus 3 actually has two different functions. So we are going to separate it into integral from 2 to 3, because as you can see at 3, right, the function changes, right? So we have from 2 to 3 of x over 2 minus, and the actual expression between 2 over 3 of our absolute value is 3 minus x dx, and then plus integral from 3 to 6 of x over 2 minus x minus 3 dx. So then here you have to do the algebra, so you get integral from 2 to 3. If you open the parentheses, it's x plus x over 2, so it's going to be 3x over 2 minus 3 dx, plus integral from 3 to 6 of negative x over 2 plus 3 dx, and I think this piece you can compute on your own. Compute yourself. Because I want to do another type, the one where we integrate with respect to y. So as you can see, the graph now, before it was something like this, right? So when we were drawing the rectangle, the length was over y-axis, so that's why we said f of x minus g of x. Well, here, the way the graphs are, I cannot draw a rectangle, right? I cannot draw that because it's not connecting the two functions, so it's not going to help me. So because of that, we are going to integrate with respect to y. So our formula is still going to be very similar. The area is going to be integral, but it's going to be across y, so whatever e to d to e, for example, or c to d, we had a to b, and then it's going to be whichever function is to the right, so f of y minus whichever function is to the left, g of y dy. So while in this part was the function that was higher, right, up, minus the one at the bottom, right now we have the right minus the left. So let's take a look at this problem. So I'm going to pause it and make the graphs to find the area. So I graphed in red so we graph it, and we found that the area that we want to find is the one that we shaded in black here. So how do I find the area? Well, we can also use the method that we learned, where we are actually going to draw a rectangle like this. But let's not forget that the whole point was to integrate, to find the area around with respect to y. So I'm gonna make the rectangle that we want to find is gonna look something like this, right? So the blue one. So now, where do these intersect in terms of y, right? So they intersect here, and they intersect at the origin. So let's do that. If we set y equals to y squared, right, because it's x equals and x equals, so we are thinking exactly the opposite what we were doing before, right? Before we had y equals something, and now we have x equals something. So if we compute this, if we move the y on one side and if we factor it out, we can easily see that we get y equals 0 and y equals 1. So our integral, the area, is going to be integral from 0 to 1 of the function that is to the right, is that linear one, so it's x equals y, so we'll put y minus, and then the curve one is y squared dy. So we get y squared over 2 minus y to the third over 3. These are the antiderivatives from 0 to 1, which is 1 over 2 minus 1 over 3, which is 1 over 6. And if you know me, you probably already know that I like to solve problems in more than one way. So I try to solve the same problem with respect to x, like we did before, like you looking at the red rectangle. So what I did, I rewrote the function of y equals x, and then we had x equals y squared, so y can be plus minus square root of x. But I've used just the positive one because we are using the area only in between in quadrant 1. So when we set y equals x equals to y equals square root of x, so if we set this equal to each other, we get x to be 0 and 1. So the area that we want to find, this time it's integral from 0 to 1 of square root of x, because the curved graph, it's above the linear one. So I set up the integral, and then when we calculate it, we get 1 over 6, which is the same as we got above. Well, I hope this helps.